6, I counted duals of two formulas, like
that's it, yes.
dual of B mu nu.
Yeah, yeah.
But then when I'm not looking at the moduli fields, not scalar, but the full all degrees of freedom,
Yes.
once I've counted B mu nu's dual in moduli field list, I will not consider B mu nu as an independent.
No. Yeah, so you will not think of B mu nu as an independent field, you just think of this as a scalar field. Right? You can use B mu nu as an independent field, but this it's often more for, particularly for supersymmetry, okay, it's often more convenient to think of B mu nu as a scalar. Right? Because typically when you try to write in terms of the superfields, for example, the dilaton and this dual of B mu nu combine to become a scalar superfield.
So, that's what I was getting on to when you in the beginning listed the field contents of different supergravity.
Yes.
You considered B mu nu in the
yes, in higher dimension.
Considered the dual in some other.
Yeah, but that was in 10 dimensions, right? In 10 dimension you use the B mu nu, because in 10 dimension if you dualize B mu nu, it will be a big tensor, right? It's only in, after you have come down to 4 dimension, it's useful to dualize B mu nu into a scalar. You don't have to do it, right? It's just it's more convenient in 4 dimensions. Yes.
This is about modular fields. So suppose you take the gauge field for some not for some group set. So we have these commutator terms. So basically, when you reduce gauge fields to say one circle, then it becomes adjoint scalar.
That's right.
So there is a for one f term, say f the compactified direction and non-compactified direction with this index. So there is a commutator term which is like commutator phi and some ai.
Yes.
Right? So if I choose to give non-trivial values to these AIs, gauge fields, cannot this generate a potential for the phis?
No, but AIs you don't give I mean those are gauge fields, right?
If I choose to take a non-trivial value in the value.
Yeah, so then that you don't call this a potential, right? It's like if you have a charge scalar, right? Suppose you have a scalar that is charged under a gauge field. Okay, so then there is a d mu phi mod square, right? That's precisely the term that you are seeing, right? But if the gauge fields, but phi can still have a vanishing potential. D mu phi mod square, existence of a term like d mu phi mod square is not inconsistent with phi having no potential. Right? You don't call d mu phi mod square as a potential term. Right?
Yeah, but there is a commutator phi a term, right?
No, it's not there because there is only one phi. If you have a mu with a y mod square, right? Okay. So this term is not a potential for a y. This is a gauge field, right? This is part of, when you write the low energy theory, it will be like it is part of this term, right?
Yeah. No, but suppose in the vacuum if I give mu a value.
mu.
Yeah, this mu.
Yes, because this of course then it will be generate a potential d mu minus I mu times phi square. And if you give mu a value, it will generate a potential.
Yeah, you normally do not call these things potential, but then won't it restrict phi not to take some arbitrary constant values?
No, because mu can be 0. Vacuum is characterized is Lorentz invariant, right? You don't say switch on mu vacuum expression value in the vacuum, right? In the vacuum mu is 0, phi can take then arbitrary value expression value. When there are more than one circle, then of course the commutator term comes as part of the potential, and then you have to make sure that you don't generate a field strength. But if there is only one circle, then you don't have that restriction. Yeah, any other questions? Yes.
Like this in the heterotic SO32 and E8 cross E8, to understand the duality, there had to be non-trivial background gauge fields.
That's right.
But then, and only then the duality can be realized.
Yes, that's right.
If we consider that background.
Yeah, which basically means that in the moduli space, because the expectation for the background gauge field, it's not background gauge field, it's a background scalar field from the point of view of the 9-dimensional theory, right? Okay, so which means that in the moduli space, these two theories are connected. Okay? Because the moduli space is parameterized by the radius of the circle, as well as the vacuum expectation value of that gauge field, right, which behaves like a scalar. So in this moduli space, you can move continuously, okay, from a region where you have E8 cross E8 gauge group in 10 dimension, 9 plus 1 dimension, that corresponds to the radius goes to infinity limit. Then you can move continuously to the another limit in which you have SO32 in 9 plus 1 dimension, right, where the corresponding SO32 radius goes to infinity. But in this process, right, in order to move from one end to the other end, you have to switch on non-trivial expectation value of the gauge fields. Right? But otherwise, it's impossible to go from E8 cross E8 to SO32, right, because they have different gauge groups. Right? So you first have to break the gauge group, right, and then in appropriate limit, you recover a different gauge group.
So my question is, in view of this fact, in the duality network that you've shown, like the connections between,
Yes.
I mean, how can I be sure that there is no, I mean, is it exhaustive, like there might be other kind of expectation values given to some other fields which will recover some other duality?
Yeah, the point is that as long as there is no, the number of supersymmetries is different. See, giving constant expectation value to the fields do not break supersymmetry, right? So right now we have these two different sectors, right, the M theory and type 2 and type 2b, and the other side heterotic, the two heterotics and type 1, right? Those cannot be connected, right, till you break supersymmetry, right? But this can be done. I mean, for example, M theory on an interval, right, which is an orbifold of a circle, that is dual to any 8 cross 8 heterotic, right? But just by circle compactification, you cannot relate those two sectors.
No, but I was being confused with the fact that I'm giving some background values to some scalars or some gauge.
Yes.
How do I know that there are no other that assignment of background values which will reveal some other kind of dualities maybe within the same sector?
Yeah, it can happen. Right? So this is something you have to analyze by looking at the spectrum of the theory. Right? Because spectrum and interactions, right? As a conformal field theory, you can ask what are the possible connections, right? As this is a conformal field theory moduli space, right? So there is a covering space where you ignore all dualities, right? And then the dualities basically tell you that this point in the moduli space is identified to that point in the moduli space, right? And this you can figure out by examining first the spectrum and then the interactions, right? And what kind of symmetries are there in this moduli space, and that will tell you what kind of connections you have in this moduli space.
Is there a SL2Z symmetry in type 2A string theory?
Not in type 2A string theory in 10 dimensions, but once you compactify, right, then because type 2B has SL2Z and type 2 and type 2B are equivalent, you get an SL2Z symmetry in type 2A also. Right? And this SL2Z symmetry is basically coming from the fact that type 2A, if you can think of as M theory on S1, right? In type 2A or 11 dimensional supergravity on S1, right? Then type 2A compactified on S1 is like 11 dimensional supergravity compactified on a product of two circles. And then there is an SL2Z that acts on the torus, right? There's two circles define a torus on which there is an SL2Z. So that SL2Z is something that you see, it's a non-perturbative. From the type 1, from the point of view of the type 2A theory, it's a non-perturbative symmetry, right? Because the M theory type 2A duality is non-perturbative. Right? It's only in the strong coupling limit of type 2A that you see the M theory at the 11 dimensional supergravity. So at the level of the effective action, you will see this symmetry. Right? But to claim from there that it is an exact symmetry of type 2A string theory requires more checks. Right? And many such checks have been performed, but none of these non-perturbative dualities have been proven. Right? That is because you don't know how to deal with non-perturbative string theory from first principles. Any other question? Okay. So for reasons that we discussed last time, while compactification on torus gives a good low energy theory at lower dimensions, okay, they are not the kind that we want for making connection with nature, okay, because they don't have they have too much supersymmetry, they don't have chiral formulas and so on. Okay. So for this you have to look at more complicated compactification, and these are provided by what we call Caravia manifolds. This is a generic name for a class of manifolds, and much of the string compactification, okay, that is studied today and which are more realistic, essentially have Calabi-Yau manifolds as a starting point. Okay, and then you can do various things with that. So for this reason, I'll now for 2 lectures I'll devote to just giving some basic facts about Calabi-Yau manifolds, what they mean and what are the various properties. Okay, and then we'll come back to string compactification again. And I should maybe give a reference. I'll just only quote the results. Okay, but if you want to know about complex manifolds, there's a book by Chern which is called Complex Manifolds Without Potential Theory. So this is not a fat book, so it's possible to read it. Okay, and most of what you'll need you'll probably find in this book about complex manifolds. Okay, so let's begin by recalling the definition of a real k-dimensional manifold. Okay, so if we take a real k-dimensional manifold, it basically is described by a collection of open sets, union of open sets or coordinate charts. Okay, so we put coordinate charts UI. Okay, these are on the open sets, and on each UI we can introduce a coordinate system. On each UI we introduce a coordinate system, choose coordinates, which take value inside a unit disk. So the UI we define by coordinate yi, which has k components because it's the k-dimensional space. So we take yi square to be less than or equal to 1. Okay, this is just a convention that we take each coordinate chart. Okay, we describe by a coordinate system which is inside a unit disk. And on the overlap, on the intersection, we have a relationship between the two coordinates, which is ym I is some function fm I of y. So this is analytic function, real analytic. For
Why you are restricting to unit disk?
well, that's just a convention. Unit disk has the topology of an open set, right? So you can always say that you will cover a manifold with open sets, and each open set you will cover with a coordinate system which takes value all the way from 0 to 1. Right? When you go outside this, you just use a different coordinate chart. Right? It's just a convention. Okay, it's not necessary. Even you could also take it to be from 0 to infinity, because topologically unit disk is the same as the whole real number, right? As long as it's less than infinity. Okay. Now on complex manifold, we have the property that on each UI, so let's see, let me write, so a twin dimensional real manifold is an n-dimensional complex manifold if the following conditions hold. Such that the image coordinate is a function so this now is complex analytic. Okay, so the function relationship, first of all you have to be able to introduce complex coordinates, okay, which is not hard. Okay, on a inside a unit disk, any set of real numbers can be combined into two n real numbers can be combined into n complex numbers. Okay. But on the overlap, the transition function which relates the coordinates in one chart to coordinates in another chart must be complex analytic. Okay, so this is the strong condition that this function is complex analytic. Is this okay? So on a complex manifold, one introduces the notion of a complex structure which plays an important role. Complex structure J. I like define it more precisely. This effectively corresponds to multiplication by I. Of Z by I. Or equivalently, let me write it as tangent space del Z Im by minus I. Okay, so you can think of complex structure as an operator, a linear operator on the tangent space, okay, and the way it acts on the tangent vectors is that it takes the tangent vectors del Zmi and multiplies by minus I. Okay, that corresponds to multiplying Zmi by I. Okay. And del Z bar Mi, it will multiply by I. Now, it is easy to see that this complex structure transforms correctly when you go from one coordinate patch to another coordinate patch. Okay, so let's see. So if we take ui intersection uj, then del Zmj is del, let me write this relation. So Z Ji is Fmi of Zj, right? This was what I had introduced. So we can write this as del Fmi del Z n J Okay, so on the overlap, you can transform the tangent vectors in this way. This is just a chain rule of differentiation. Okay, del Zmj is equal to delZni, del Zmj, del Zni. Okay, and Zni has this form. Okay, I can put this to be n on both sides. So because of this, we see that there is no del Z bar here. Okay, so if we multiply this by I, that's the same as multiplying this by I. Okay, so on the overlap, okay, this operation of multiplication by I, okay, goes over to the operation of multiplication by I as you move from one coordinate chart to another coordinate chart. Okay, because del Z is a linear combination of the del Z's and no del Z bar. Okay. That would not be the case if this depended both on Z and Z bar. Okay, unless the transition function was holomorphic, there will be an additional term here which will also involve del Z bar. Okay, absence of that tells us that the multiplication by I commutes with the operation of going from one coordinate chart to another coordinate chart. Is this clear? Now, this looks like a trivial statement when you use complex coordinate system, but you can also, once you know what J does, okay, it acts on the tangent vector this way. Now, a complex manifold you can also write in a real coordinate system. Okay, in the real coordinate system, we will write the tangent vectors as del xi, where I runs from 1 to 2n. Okay, and then J will still correspond to some linear operator on the tangent space. Okay. So the complex structure, what we are calling J as multiplication by I, okay, can be regarded even in the real coordinate system as some operation, some linear operation on the tangent space. Okay. So how do we recognize that it's a complex structure? Right? Suppose I give you some arbitrary linear operator in the tangent space. Okay. Is it guaranteed that it corresponds, that it can be thought of as a complex structure? Right? Namely, there is some choice of coordinate system, okay, such that the tangent vectors J will appear as multiplication by I on the tangent vectors. Okay. So, in real coordinates, J is some linear operator on the tangent space satisfying two conditions. First, J square is minus 1. Okay, you can see that is why it has to be the case, because multiplication by I means if you operate twice, it should get multiplied by minus I, right? And this is true whether you multiply by I or minus I, right? Because the tangent space is spanned by del Zi and del Z bar, right? On del Z bar I, you are multiplying by minus I. On del Zi, you are on del Z bar I. Sorry, on del Zi you are multiplying by minus I. On del Z bar I, you are multiplying by I. But on both set of vectors, when you square J, it should act as -1. Okay, so j square should act as -1 on the tangent vectors, an arbitrary tangent vector in the real coordinate system. Okay. But this is not enough. Okay, having j square equal to -1 does not guarantee that you can actually introduce complex coordinates satisfying all the analytic properties. So there is furthermore a differential equation on J. Equation on J. Okay, which I will not write down. Okay, it's called the vanishing of the new tensor. And the point is that once, if somebody gave you a real manifold, okay, and an operation J, linear operator J on the tangent space, everywhere satisfying j square equal to -1 and this differential equation, then you are guaranteed that you can introduce complex coordinate system on that manifold. Okay, but this is necessary. Okay, that you can introduce a complex coordinate system on that manifold on which j acts as multiplication by -I on del del zi's and multiplication by +I on del del z bar i's. Is this clear?
Are these necessary and sufficient conditions?
Yes, so these two are necessary and sufficient. Okay. So if you just have this condition, right, this is what is called an almost complex structure. Okay, that you have a linear operation on the tangent space, okay, whose squares to -1. Okay. This is not enough to guarantee that there is a complex, that it's a complex structure. So it's called an almost complex structure. Okay, and once you satisfy the second condition, it becomes a complex structure. Okay. So this condition basically essentially is the analog of the Cauchy-Riemann condition. Right? We know that when you introduce z as x plus iy, for example, right, then the analytic function of z will have to satisfy certain differential equations. Okay? And that differential equation translates to an appropriate differential equation to be satisfied by J. Okay. So let's work out an example. Let's take the simple case, z equal to x plus iy. So in this case, x will be half z plus z bar and y is z minus z bar of y. So del del z is del x del z times del del x plus del y del z times del y. I am just converting into the real coordinate system. So this is del x del z will be half del del x and del y del z will be plus 1 over 2i or say minus I by 2 del del y. Okay, so now del del z going to minus I del del z means that half del del x minus I by 2 del del y goes to minus I by 2 del del x minus I minus half del del y. Okay, so effectively del del x goes to minus del del y and del del y goes to del del x. So in the matrix form, I can write del del x, del del y goes to 0, minus 1, 1, 0. Del del x, del del y. Okay, so this is our complex structure. Okay, in this case it does satisfy the differential equation because after all, if it's constant, right, then any derivative acting on this will be zero. And you can easily see that j square is minus 1. Okay, as okay. Now, one of the important points is that given a real manifold, okay, say 2n dimensional real manifold, it may admit more than one complex structure. What it means is that there may be more than one way of introducing a complex coordinate system, okay, which cannot be transformed into each other by analytic change of coordinates. Okay, that's what I mean. The two real manifolds may be same as real manifold, okay, which means that by real analytic change of coordinates, you can make the two real manifolds the same. Okay, but by complex analytic change of coordinate system, you may not be able to make two complex manifolds the same. Okay. So here is a simple example. So let me first write the statement. So two manifolds which are same as real manifolds may be different as complex manifolds. So here is an example. So take a two-dimensional torus. So it's basically characterized by two coordinates, two real coordinates, y1, y2, which is taken to be equivalent to y1 plus 2 pi y2 and also y1 y2 plus 2 pi. Okay, so basically a square with opposite lines identified. Okay, shift by 2 pi in the y1 direction and shift by 2 pi in the y2 direction are identified. So you can imagine that you basically fold it, make it into a cylinder and then fold it to make it into a torus. Now, suppose we introduce coordinate system z as y1 plus tau y2. But tau is a complex number, tau 1 plus I tau 2 with tau 2 positive. And we declare these are the complex coordinate. Now this of course is not doesn't cover the whole coordinate patch. Okay, so the identification now is shifting y1 by 2 pi, sorry, I should say z plus 2 pi, and this is z plus 2 pi tau. So shifting y1 by 2 pi, shift z by 2 pi, shifting y2 by 2 pi, shift z by 2 pi tau. Okay, so z is not a global coordinate system, okay, but you can introduce coordinate patches, okay, and cover the torus by in coordinate patches which are related to z by analytic change of coordinates. Now it's easy to convince yourself that for different tau these give different complex structure. Okay, there is no analytic change of coordinates that we can make in which an identification like z equal to z plus 2 pi or z plus 2 pi tau becomes z equal to z plus 2 pi equal to z plus 2 pi tau prime. Okay, that means a change of coordinates is not possible. Okay. Which will basically mean that for different tau, we have different complex manifolds. Okay, they are different in terms of complex topology. There is no change of coordinates that can relate manifolds for different tau. Okay. Except for certain changes, for example, if you take tau to tau plus 1, tau and tau plus 1 are equivalent. So we can find appropriate coordinate transform which does that. Tau goes to minus 1 over tau is also equivalent, but that's all. Okay, this I will leave as an exercise. So exercise, take the different tau. Tau gives different complex structure. Okay, which basically means that it's impossible to find a coordinate transformation that relates these two different tau. Okay. But of course, as a real manifold, they are clearly the same, right? In fact, when you use a real coordinate system y1, y2, you don't even know about the existence of tau. So obviously, all of these they describe the same real manifold. Okay, the square torus. Okay. Let me repeat, remind you that here you are not talking about metric, right? When you are thinking of the topological properties, okay, there is no notion of metric. So the square torus is just means that it's topologically this square torus, not that it has a metric which corresponds to this square. Is this clear?
So,
Yes.
in the definition of J,
Yes.
had we taken the minus sign to the other one, I mean in the anti-homomorphic, if there was a negative sign,
Yes.
that would have led to the same J square is equal to minus 1.
Yes. So basically that takes j to minus j. Right? If j satisfies the relation, then minus j also does the same.
Oh.
Right? So that's a trivial change. Right? Whether you call j as the complex structure or minus j as the complex structure is not really very much relevant.
Also, there's the complex half plane and the complex plane, the full complex plane. There are also instances of real manifolds which are not same as complex manifolds.
Let's see, complex half plane and complex plane. It depends on in complex half plane whether because one gives the disk, the other one gives the sphere. Right?
Yeah, right.
Because when you take a complex plane and identify a point at infinity, you get a sphere. Whereas for a complex half plane and point at infinity, identify you get a disk. So they are also defined as real manifold.
Suppose you don't have that, then I mean then also it's I mean even though then they're the same as real manifolds, right? If you don't have a point
real
at
line is the
infinity.
boundary of the upper complex plane. So
Yeah, so it depends on whether you include a real line or not, right?
Open half plane. The open half plane.
Yeah, because the open half plane it has the topology of a disk, right?
Yeah.
Which is the same as the full plane,
Full plane.
right?
But the thing is, complex manifolds they probably will be different.
That's true, yeah.
One is
Yeah.
hyperbolic and the other one
Yeah,
is.
exactly. But we will be considering mostly compact spaces, right? For non-compact spaces, things are a little more subtle, right? At least many of the later notions that we'll be introducing will be valid only for compact spaces. So we'll stick to compact spaces. Okay? And for compact spaces, we can clearly see the difference here. Okay, the torus is the simple illustration that two manifolds which can be the same as real manifold but not the same as complex manifolds. Okay, so in a sense, complex structure gives a finer topological classification than just having a real structure.
given a even dimensional real manifold, isn't it simple check to see whether it admits a complex structure or not? I mean, not trial and at all. But
Well, it has to be orientable, right? Yeah, I mean, I think the problem is that once you have an orientable real manifold, locally at least you can introduce complex structure, right? Globally there may be abstractions, right? Which I mean, there are probably some topological properties you can study.
yeah, can one study certain quantity then say that well this is non-zero so it doesn't allow what?
Some topological property. You have to study, right? For example, if it's not orientable, then you know for sure
Yeah.
that it cannot be a complex manifold. Right? Orientability is definitely something that you need, not just the evenness of the dimension.
But even after that also it may have
Even after that, there may be obstructions if the manifold is sufficiently complicated, but I am not completely sure. Okay, whether there are other possible obstructions that can arise.
Like patch by patch, if the Newton's tensor vanishes, one is guaranteed.
Yes, but that's yeah, patch by patch. Well, no, I think
Beyond that, doesn't one.
yeah. Even then, there can be global obstructions because
But if I can match it for every patch, check it for then I'm down. Nothing else.
I think even then you are not done because okay, the point is there are two things. One, the J has to be a tensor,
Yeah.
right? So global obstructions are arise in that case. Yeah. So as long as J is a tensor, which is a global property,
Yeah.
right?
Then
And the
if I
Newton's
check patch by patch, then I'm
exactly. Yeah, and the Newton's tensor vanishes patch by patch, then you are out. Exactly. Okay. Because otherwise I was thinking that if you take Klein bottle for example, right? Locally it's indistinguishable from a torus. Right? You just make a global identification which is reverse, but what will happen is that J will not be a tensor in that case.
Because at one point the map, I mean, it will be.
J will be then to
minus one for
exactly. That's
the
it.
Jacobian.
Orientability basically means that we can define a top dimensional form which is nowhere vanishing, right?
Exactly.
So that is a symplectic form, and using that we can define.
Yeah, probably you can define a
define a
complex.
J.
Yeah, locally. Yeah, exactly.
Now, one more thing, I mean, there is this symplectic manifolds, those are also allowed in even dimensions and complex tensor also. Are there some simple statements like all symplectic manifolds are complex?
Yeah, I'm not sure. There may be something, but it may not be.
As long as there is a metric, I think we can go from one to the other. Like Gu, comma JV is equal to the.
Yeah, you are not assuming right now that there is a metric.
Yeah.
None of the definitions
Without-
require metric.
What?
None of the definitions of complex manifold or
Yeah,
symplectic
exactly.
manifold require a
That's
metric. So,
Yeah.
But if there is a metric, then they equivalent.
Then you can try to connect them. Yeah. Okay, so now let me talk about metric on a complex manifold. So general form of the metric without any restriction has the following structure. Okay, I have just written the metric in the complex coordinate system, but it's basically the same as Gij or Gmn dxm dxn. Okay, if xm's are a real coordinate system. Okay, reality. So ds square of course is real, and this basically requires that G alpha beta bar is G beta alpha bar star is complex conjugation. And G alpha beta star is G alpha bar beta. And of course, G alpha beta is symmetric, and so is G alpha bar beta bar. Okay, this has no symmetric property. G alpha beta bar has no symmetric property. Okay, so this metric we'll call Hermitian. So metric is Hermitian if the following condition holds: G alpha beta should vanish, and as a consequence, of course, G alpha bar beta bar should also vanish. Okay, so Hermitian metric is the one where only components are G alpha beta bar, dz alpha, dz beta bar. Taylor metric is Hermitian. Okay, the first condition of course is with an additional condition, namely G alpha beta bar should be del alpha del beta bar k z z bar on each coordinate match. So locally, you should be able to write G alpha bar to beta bar as del k, del alpha del beta bar, k z z bar. Okay, this is the definition of a Taylor metric. But this function k need not be a globally defined scalar. So on the overlap ui intersection uj ki is a function of zi z is kj zj zy plus in general some function fij of zj, sorry, fij of zj plus gij of zj. Okay, so let's see what it means. So basically what we are saying that on each coordinate patch locally, G alpha bar beta bar has to have this structure. Okay, there should be some scalar that you can define locally. So G alpha beta bar is this. However, when you have two overlapping patches, okay, suppose Ki is the corresponding Taylor potential. So this is called a Taylor potential. So suppose Ki is the Taylor potential on the ith chart, Kj is the Taylor potential on the jth chart. Then Ki and Kj can be equal, of course, but the more general situation is that when they differ by the sum of a holomorphic function and the anti-holomorphic function. Okay. And it's easy to see that these functions do not contribute to the metric, right? Because this involves a holomorphic derivative and an anti-holomorphic derivative, so these don't contribute. Okay. And it's guaranteed that the metric, if this relation holds, then it's guaranteed from here that the metric will transform as a tensor, as it is supposed to. Okay, as you go from the zi coordinate system to zj coordinate system.
Given a Hermitian metric, in each single patch one can solve for k, right?
No, so Hermitian metrics are not necessarily Taylor.
But in a single patch, not maybe on the whole main.
So even in a single patch, if you can do it in each single patch, then of course you can do it over the whole thing, right? And then on the overlap it will be related by this. Right? So even in a single patch, hermiticity only means the G alpha beta is 0, right?
Yeah.
Okay. But this requires more. See, for example, this will require that del gamma del G alpha beta bar is the same as del alpha G gamma beta bar, right?
Yeah.
That need not be the case. That's the integrability condition which may be violated by them. So it's not guaranteed that the Hermitian metric will always be Taylor. But Taylor metric by definition is Hermitian and it has this structure.
So K has to be real, right? Or then that forces G to be F
Yeah.
bar, right?
If you can imagine that K, you can include in K some complex thing which is of this form.
So K can be, need not be real, is it?
Well, it need not be real, but the amount by which it fails to be real must be of this form, right?
That is allowed.
That is allowed because normally you can say that you take K to be real, but
Because I want a metric to be.
yeah, well, yeah, metric to be real, but what I'm saying is that if K has some imaginary piece which is of this form,
We'll cancel it.
will cancel out. It will not contribute to the metric. Right? The metric also has of course has to satisfy this condition.
That forces K to be 0.
Yeah, exactly.
But the sheaf doesn't matter because it cancels in the metric.
Yeah, exactly. It cancels out in the metric. So given a K, you can always add arbitrary terms like this, right? Because there is no independent definition of K anywhere on each coordinate patch. Right? Suppose you have found a real K which produces the metric. You can always add two terms, a holomorphic function and an anti-holomorphic function, which have nothing to do with each other, to K. Right? It is still a perfectly good K, right? And that's not necessarily real.
But generally, in the literature for the scalar transform, this potential transform, people take, F plus F bar. Is there a reason or?
Yeah, because the point is that that's a convenient thing to do, that you say that you make it real by simply removing all terms like this, right? When F and G are different.
But there was no need for that.
There is no need. It's just a matter of convenience. Okay, so if you want, you can fix K to be real, right? And in each case, as long as K is real on each patch, then F and G have to handle conjugates of each other. Yes.
Can K always be written as just the sum of something Fi and Gi? Without the first piece.
No, then the metric will be trivial, right? Then the metric will vanish. Because if A is just sum of these, then it doesn't, metric is identically 0, right? That you certainly don't want that. Okay, so next I'll introduce the notion of holonomy. Okay. This is in fact a notion that you can also introduce for real manifolds. It's not necessarily true for complex manifolds. So let me give a more general definition and then I'll return to complex manifold. Okay. So suppose M, you have same manifold M is some real manifold. So let's take a point P in M and take an arbitrary curve C also in M, but that passes through P. Okay. So, and this is oriented, we take this to be oriented. So suppose we start with some tangent vector, not tangent to the curve, okay, some tangent vector A. So A is some tangent vector okay, so tangent vector, by tangent vector we mean that it's a some vector, arbitrary vector in the tangent space of P. Okay. Now, using notion of parallel transport, we can parallel transport A along this curve. Okay, this is of course true if you have a metric. Okay, let's suppose that you have a manifold with a metric. Then we can parallel transport A along this curve C and come back to P. So during this parallel transport, okay, typically it will come, A will come back to a different vector, A prime. Okay, so parallel transport around C, parallel transport along C will change A to some other vector A prime. But A prime is related to A by a linear relation. Some matrix R C can say. Okay, some matrix, because of course the relation is linear, right? Parallel transport is a linear equation. Okay, it's a linear differential equation. So what it will come back to is some matrix, okay, which is a 2n by 2n matrix or n by it's a matrix whose dimension is the same as the dimension of the tangent vector, tangent space and same. So this is known as the holonomy along C. Now, if we are considering a Riemannian manifold, then RC is part of H of 2n. It's a 2n dimensional Riemannian manifold. 2n dimensional. Okay, in general the dimension need not be even. Okay, but we are taking 2n because eventually we will be restricted to complex manifolds. So if it's a 2n dimensional real Riemannian manifold, then you know that the norm of the vector is preserved under a parallel transport. Okay, so we get RC to be part of S of 2n. Well, it could be O to n if this card is not contractible. Okay, so that's a more general situation. Let's take S of 2n for now. Now, if we take the collection of RC for all possible C through P, cards C through P, then they form a group under multiplication. Okay, so how do you see this? So how do you have to show this? You have to make sure that if we have, suppose you have some curve C, right? You get a holonomy, we get this matrix RC. Imagine that you have another curve C prime. In order that they form a group, RC times RC prime must also be in this set. Okay, so it means you have to be able to identify another curve through P for which the holonomy is RC times RC prime. That's not hard to see because the curve through P which gives you this as the holonomy is C dot C prime. So this means that we first follow C prime and then C. This is also a path through P, right? So imagine that you have two paths. One is C, the other one is C prime and C. Okay. So then, if you want to see what the tangent vector does, take a tangent vector, first transport it around C prime, then transport it around C. This is a perfectly good path through P. Okay, because they are supposed to, so the holonomic group involves collection of all possible paths, right? Collection of all RC for all paths. So going around C prime and then going around C is also a path. But what will be the holonomy around this? So for the tangent vector, when you transport around C prime, you will get multiplied by RC prime. Right? Then when you transport around C, you will get multiplied by RC. Okay? So this relation is automatic. Okay, so this we have identified then the specific curve which gives you the product of these two elements.
This is a subgroup of S of 2n.
It will be subgroup of S of 2n obviously because each RC is belong to S of 2n, right? So this is a subgroup of S of 2n. Okay. We also have to show the inverse, right? What is the inverse in this case? So RC inverse
Going back, I mean,
going backwards, right? So these are oriented. So I'll call this R of minus C. So minus C will mean C in opposite orientation.
This collection, it can include the homotopically distinct curves.
Yes, it could. The holonomic group of a manifold includes all possible curves, right? Including those which are not compactable. Okay, are there any other questions?
For pseudo-Riemannian manifold will be SO 1 to n minus 1.
For?
For Minkowski, I mean with time and space.
Yes, if you have time and space, then it will be SO 2n minus 1 1. Yeah, exactly. But we will be applying it only on the compact part of space time. Right? So for that, that's why you have to be here. Okay, now from the definition itself, it's clear that because you are taking the collection of all paths, right? Whereas the holonomic along a given curve, of course, depends on the curve. Okay? Holonomic group is independent of the curve, right? Because you are taking the collection of all possible curves. What is not completely obvious, but it's true, is that the holonomic group is independent of the choice of P. The way you have defined it, okay, we take all paths through P and collection of those we call the holonomic group. Okay? Collection of those elements. All paths have to pass through P. But imagine that we consider another path, P, another point P prime, and consider all paths through P prime. We can define a holonomic group corresponding to the point P prime. Okay. Is it the same as a holonomic group that we got from P? Okay, one can say that indeed they are the same. Okay. I will not go into the details, but you can try to prove it. Okay. The general strategy is that given a path through P prime, okay, you can associate with it a path through P by simply going from P to P prime, going around that path and coming back. So given any path through P prime, you can find a corresponding path through P and vice versa. Okay, given a path through P, so draw some arbitrary curve. Keep it fixed once and for all, some C naught. Okay. Then imagine that you have some path through P. Okay, we want to associate with it some path through P prime. Okay. You go along C naught, go like this and then come back. Similarly, if given any path through P prime, we can associate the path through P by going here, going around this and coming back. So this way, we can make a one-to-one correspondence between the path through P and the path through P prime. And one can show that this one-to-one correspondence, okay, what it does to the matrix, to this RC, is essentially conjugated by a fixed matrix. Okay, that fixed matrix is the matrix that will pick up in going from here to here. And you know that under conjugation, the group doesn't change. Right? How you embed this holonomic group in the SO2n may change, but the group itself will remain the same. Okay, so that's the proof that holonomic group is independent of the point, choice of the point. Okay?
The manifold to be connected.
Connected, yes. Of course, if the manifold is not connected, if you have a torus and a sphere, then the holonomic group on the torus may be different from the holonomic group on the sphere. The manifold has to be connected because you have to find a path from P to P.
In general, is it true that you can quotient out something and then, I mean, by quotienting out something, you can get the fundamental group from the holonomic group?
Yeah, you can get it probably, yes, because
I'll probably take the holonomic group for all the contractible.
exactly, yeah.
And then quotient that out.
Yeah, I mean there are elements whose n multiple for example is trivial. Right? The holonomic may still be non-trivial around those curves, right? But in terms of the homology, that's a trivial curve. Okay, but I should add that the holonomy is a property of the metric. Okay, it depends on a metric, whereas many of the topological properties that we have been talking about earlier are independent of the metric. Okay, so this is an important distinction to keep in mind. Okay, so you know that the holonomic group has to be a subgroup of SO2N. Okay. Now one can show, I will not show it, but I will just take the result. That for a complex scalar manifold, well, it's probably true also for Hermitian, but for a complex scalar manifold. Dimension 12. So the holonomic group for a complex scalar manifold, of course it has to lie inside SO2N, okay, but one can show that it actually lies inside UN. Okay. Now it's not hard to see why this is the case. Okay. This means that if you split the tangent space into two parts, okay, one spanned by del del zi's and the other spanned by the del del zi bars, okay, then the del del zi's come back to del del zi's multiplied by some complex matrix, and del del z bar I come back to del del linear combinations of del del z bar I. Okay. The del del zi and del del z bar I don't mix. Okay. So if you take the tangent vector del del zi and parallel transport it, okay, it comes back to a linear combination of del del zi's. Okay, that's what it means, that it's part of UN. Okay, this is something you can show explicitly. Is this statement clear? So basically what happens is del del zi goes to u I j del del z j. So U to begin with is an arbitrary complex matrix, but because it has to preserve the norm, because after all it's a Riemannian space, that forces U to be part of UN, not an arbitrary complex matrix.
So does it go the other way around also? Like if the holonomy lies in this, then it's a scalar manifold?
This I am not completely sure. Right? You may be able to cook up manifolds where the holonomy lie in this and it's still not scalar. I am not completely sure whether it goes the other way.
In 2 dimensions, I mean n equal to 1, u1 is equal to SO2.
Yes.
So in that case,
yeah, in that case, of course, in 2 dimensions, every manifold is a complex manifold, right? As long as it's orientable. Right? Yeah, I think it is not true in general in higher dimension even after orientability, right? That every even dimensional manifold is a complex manifold. But I'll try to check what the abstractions are. In 2 dimension, it is true that every 2 dimensional manifold which is orientable is a complex manifold.
See, in this case, if all loops are contractible, then it would be SU-N, is it? That like you had SO2N. This also includes the case where it's not.
No. For example, the sphere. the holonomic is U1, right? Not SU1. SU1 is trivial.
Sir, I mean for higher dimensions, is it?
Even higher dimension, I think it's even if the curve is contractible,
It's still U1.
right? It's still U1. CPN, for example, has a holonomic group in UN, not in SUN. Okay, in fact, SUNs are spatial, so I'm just coming to that. So now, definition of Calabi-Yau manifolds. So these are complex manifolds. Which admit scalar metric SU and okay. So now note the following, that the notion of a manifold, a complex manifold, it doesn't care about a metric, right? It doesn't have to have a metric. Okay? Complex manifold is defined without a metric. Okay? So Calabi-Yau manifolds are complex manifolds by definition, so it doesn't necessarily have to come with a metric. Okay? The definition of a Calabi-Yau manifold is that it's a manifold of the kind, okay, where it is possible to put a scalar metric with SU and holonomy. Not all manifolds have this property. There are some manifolds, for example, sphere, okay? A two-dimensional sphere. That's a complex manifold. You can put any metric that you like. Okay? You don't have to say what from the beginning what metric you have chosen. But that's not a Calabi-Yau manifold, which means that it's impossible to put a metric on the two-dimensional sphere which has this property. So this distinction is important. Okay? Calabi-Yau manifold necessarily do not come automatically with a metric, with a scalar metric with SU and holonomy, but it is in principle possible to put a scalar metric with SU and holonomy on a Calabi-Yau manifold. Okay, this distinction will be important later.
So the difference with the sphere is then the sphere can also have a scalar metric, but the holonomy is U1.
Yeah, so if you have a two-dimensional sphere, right, then the holonomy in this case is U1 or SO2.
Yeah, sorry.
Okay.
A torus would be Calabi-Yau manifold.
Yes, so torus will be a Calabi-Yau manifold trivially, right? Because
you can put a trivial metric and then the holonomy
exactly.
will just be.
So on a torus, right, the metric you can take to a flat metric, right? Holonomy is trivial. Right? U1, SU1 is also trivial, right? SU1 as a group is trivial group. Right? So torus, in fact, is the only example of a Calabi-Yau manifold, which is two real dimensional or one complex dimension. So let me do this.
One more thing, this
Yes.
holonomy of a manifold, does it care about the topology of this manifold or it's locally?
No, so holonomy is a property of a metric that you put on the manifold. Because without putting on a metric, you don't know the notion of parallel transport, right? So holonomy is a property of a metric. Okay? But the ability to put a scalar metric with SU and holonomy, this is SU and holonomy, of a SU1 holonomy. So SU1 means what? Trivial, right? No holonomy. Which means you have to put a flat metric. And you know that it's impossible to put a flat metric on the sphere. Right? So that sort of shows that a sphere is not a Calabi-Yau manifold. Okay? Not a two real dimensional Calabi-Yau manifold. The torus is. Right? Because on the torus you can put a flat metric, and that's a Calabi-Yau manifold.
So this side is not true for Hermitian.
Which?
And this scalar can you replace by?
Yeah, probably you can replace the scalar by Hermitian. Okay, this I am not completely sure, but we can check this. Well, if you look at this book by Chern, I am sure you will find that.
But which connections are zero and non-zero, that may be important in this context. And scalar metric.
Scalar metric has more properties. I mean, certainly, finer properties, right? Because you need this property, right? The del del Zi should come back to linear combination of del del Zi, right? Now, how much of the property of the metric you need, whether you need the scalar metric, I am not completely sure. Okay? But as I said, this you can either work out by working out the connections and see that the apparent components of the connection vanish, right? Or you can look up the book by Chern and you will find the result.
What does B scalar imply for the Ricci curvature?
For the Ricci curvature, nothing. It's non-zero in general. I mean, what it says is that the Ricci tensor has this structure. The Ricci tensor is R alpha beta bar. Right? The alpha beta and alpha bar beta bar components vanish.
For Hermitian, other components can also be there, but for scalar only this is.
Yeah. Again, I mean, this can be worked out, of course, but I don't remember now the details. For Hermitian, but Hermiticity is enough to make sure that only these components are non-zero. Right? Probably you need the scalar property because you need some, because Riemann tensor involves derivatives or metric, right? And the scalar property gives you some specific property, differential property of the metric, which is not there if you just impose hermiticity. Right? So probably you need the scalar property for getting these results.
For Calabi, it will vanish.
Yes, for Calabi it will vanish. Okay. So if we put, so let me write that. That if we use a scalar metric with SU and holonomy, then Ricci tensor vanishes. So R alpha beta bar. Okay, hermiticity guarantees already that R alpha beta and R alpha beta bar are 0. But this component, mixed component, is vanishing. So this let me write in bracket. This is also 0. Yes.
U1 can be decomposed at SU1 cross U1.
Yes, that's it.
So is the vanishing of is the vanishing of Ricci tensor does that say that the U1 vanishes?
That's it, yeah. So basically the U1 part of the connection of the holonomy, right, is encoded in the Ricci tensor, right? And when the U1 part vanishes, then the Ricci tensor also vanishes. Okay. So you can see from here why Calabi manifolds are important, right? Because it's all Einstein's equation, right? And after all, when you are trying to look for compact spaces, we want to make sure that the compact space times Minkowski space time. Okay? Suppose you have taken a 2n dimensional compact space. Okay? Then the total space, which is 2n dimensional compact space times, say 10 minus 2n dimensional Minkowski space time, that better satisfy Einstein's equation. Otherwise, it's not a pardon. Yeah, we have set all other fields to 0, say, right? If some of the other fields are switched on, then the equation would have to be modified. But suppose you are looking for a simple solution where only the metric is non-zero, all other fields are 0. Then you are looking for vacuum Einstein equation, right? And there you can see why this is important, okay? Because this does satisfy vacuum Einstein equation. Okay? So if you take a space time which is Calabi times flat Minkowski space, then it solves the equations of supergravity, as long as you don't switch on other field strengths in the background.
So we can also say that if there is a calorimetric where the Ricci tensor vanishes, then it must have SU and holonomy.
Yes, that's it. If you have a scalar metric where the Ricci tensor is identically 0, well, it's true locally, but if there are non-contractible cycles,
Yes.
then it may not happen. Right? Then those along the non-contractible cycles, you may have U1 holonomy, additional U1 holonomy.
then at least the trace of the connection, if it vanishes all over, then we can say that it will have SUN unknown.
The point is the connection is a local concept, right? That will not give you information about the.
If it vanishes everywhere.
Yeah, if it vanishes everywhere, if you can choose the connection in such a way that it vanishes everywhere, then it is true that the parallel transport will never generate a U1. But typically that's hard to implement, right? Because you have to be able to define a global form of the connection. Okay. One can certainly imagine that you start with a Calabi-Yau manifold, right, and then make some global identification which destroys SUN holonomy. Right? Locally it is still Calabi-Yau, same manifold, but you just have made some strange identification, right, along which the tangent vector doesn't get transported by SUN but gets transported by UN. That's certainly possible.
So one conclusion, in
Yes.
interacting theory, aquam also undergoes perturbative shift. As metric is a dynamic quantity in string theory, one would expect under string quantum corrections.
Yeah, so these are classical solutions, right? Then you have to do quantum effects around this vacuum.
So these manifolds will still allow for this corrected metric structure.
Yes, so these are only classical solutions, right? You have to start doing perturbation theory. You have to first find a classical solution, right? And then you do fluctuations around that vacuum, right? If you don't even have a classical solution, then you can't even start doing perturbation theory, right? So these are the starting points of perturbation theory, right? These provide a classical vacuum, and then you have to see what the quantum corrections do around this vacuum.
I mean, it may happen that they may not continue to be.
Yes, it can certainly happen. Right? Just like some of the scalars, right? Massless scalars, may suddenly get a potential, which drives it away from wherever they are. Okay?
In two dimensional compact surfaces, which are complex manifold.
Yes.
So only the toruses are the.
That's right.
Because the other things will be hyperbolic or.
Yeah, sphere for example, yeah, exactly. So the
higher general surfaces will have
negative curvature, and low sphere will have positive curvature, right? So none of them are Calabi-Yau, clearly.
So only toruses.
Only torus, exactly. So 2 dimension, torus is the only Calabi-Yau manifold that you have. But any other questions?
If it's part of the metric, then we can't assume anymore that the metric still remains separated into the fact that G alpha beta bar is non-zero.
Yes, you have to include all fluctuations, right?
So that will usually describe the fact that it's a Kähler metric, right? A general perturbation.
Certainly. So the point is that the Kähler metric, that we are using this to describe the vacuum. Just like imagine that you have a scalar field, right? What do? You go to the minimum of the potential.
Yes.
That's a classical solution.
Yes.
But then when you quantize, you allow arbitrary fluctuations of that field, right?
Yes.
That doesn't even satisfy classical equations of motion. Right? The same is true here.
Okay.
That this provides the initial classical vacuum. Right? Then you start quantizing it, and it may happen that after quantizing you find that the vacuum gets destabilized. Right? That some scalar field which are vanishing potential, right? Dilaton, for example, has vanishing potential, right? Quantum corrections could generate a potential, right, which has no minimum or no extremum. Right? Then you know that theory is inconsistent. Right? That can certainly happen. So, but this is just the starting point. Okay, that you have to have a classical solution. Okay, as we will discuss later, okay, these have another important property, okay, namely that they preserve part of the supersymmetry. Okay, and that is responsible for its stability. Okay, at least to a large degree. Okay, many of the terms which would have otherwise destabilized this vacuum, one can show will be absent because of supersymmetry. Okay, it is still not, completely guaranteed that the vacuum will be stable, but at least it helps in analyzing the stability of the vacuum. Okay, so far of course I have not said anything about supersymmetry, but this we will see later. Okay, why Calabi-Yau manifolds generate supersymmetric configuration.
So was T6 an instance of Calabi-Yau? The
T6 is an instance of Calabi-Yau because again the holonomy is trivial, right? And a trivial group of course is always a subgroup of SUN. Okay? So all tori, even dimensional tori, are instances of Calabi-Yau. Okay? But from T4 onwards, you have other Calabi-Yau manifolds. Okay? In fact, for 4 dimensions, right, you have basically 2 distinct Calabi-Yau manifolds. One is T4, other one is what is called K3. Okay? In 6 dimensions, you have infinite class. Well, you have many. Okay, and I think you can probably construct infinite number of Calabi-Yau manifolds. Okay, now this fact is important, that Calabi-Yau manifolds are complex manifolds which admit Kähler metric with SUN holonomy, because it turns out that even without quantum corrections, okay, forget about quantum corrections, we know that string theory has higher derivative corrections, right? Because string, when you go to the low energy limit of string theory, you don't get just Einstein gravity, you also get corrections. Okay? And because of those corrections, this is not exactly the condition you want to satisfy. Okay? This is Einstein's equation, okay? But this equation gets corrected. Okay? And what one can show is that the metric that one really needs for describing a solution to string theory is nearly Calabi-Yau, nearly this metric, but not quite this metric. Okay, you have to modify. So you cannot really choose exactly SUN holonomy manifold. Okay. Nevertheless, this topological property is important. What one can show that whatever is the modification of the Einstein's equation, okay, are such that as long as your initial manifold is Calabi-Yau, namely it admits a Kähler metric with SUN holonomy, okay, you can systematically correct it. Okay. So the metric is no longer the metric of SUN holonomy, okay, but you can systematically correct the metric to nevertheless provide a solution to the corrected Einstein's equation, okay, or the string corrected Einstein's equation.
But will they be called Calabi-Yau? Because Calabi-Yau is...
Well, Calabi-Yau is a property of the manifold. Topologically, it's the same manifold, right? Is that the metric that you need for the relevant metric that you need for string theory is not exactly the SUN holonomy manifold. For large volume, when the Calabi-Yau size is large, it is almost then the hard derivative corrections are small, right? Then it's nearly the SUN holonomy metric, okay? But there are some small correction that you have to add. Okay? But what one can show is that as long as you start with the Calabi-Yau manifold, you can always correct the metric appropriately to account for this corrections to the equation. Okay? So for full string theory, we need not exactly the Ricci flat metric or the SUN holonomy metric, but something that is close to it. Okay, so now suppose you have a Calabi-Yau manifold. So typically, what one finds is that a Calabi-Yau manifold typically admits a family of Kähler metrics each of which what does it mean? Then imagine that you are given a Calabi-Yau manifold. which means that we have given a manifold as a whose complex structure has been fixed. Okay, you have fixed a complex coordinate system. Now, given this, I have introduced the notion of a Kähler metric. Okay, but it turns out that you can get a family of Kähler metric, and in each member of the family has a metric of SUN holonomy. Okay, so in other words, given the Calabi-Yau manifold, the SUN holonomy metric may not be unique. Okay, there may be lots of SUN holonomy metric. Okay, in fact, a family of SUN holonomy metric. This family called the Kähler moduli. The other important notion is that regarded as a real manifold, a Calabi-Yau
What is the separating characteristics for each family?
what is the?
Between two families, what is the separating?
Here?
Yeah.
The Kähler potential is different. The family of Kähler potentials.
Yeah, so for each family there is a SUN.
Exactly.
Under this
For each member of the family, exactly.
When you say different, they are not weighted by something of the form Fz plus G Z bar.
Those would be
No,
the
no,
same.
those are when I say different Kähler metric, they are really different Kähler potential, right? Not related by just Fz plus Gz bar. As a metric, they are different, right? So which means that given a Calabi-Yau manifold with complex structure fixed, instead of having one SUN holonomic Kähler metric,
I am asking, suppose you have two Kähler metrics.
yes.
How you determine whether they are in the same family or different families?
Okay, in this case, the way I have said it, right, it's a crude way of saying it. Later on, we will see how to distinguish them. Okay, there is topological distinction. But right now, you are saying there is a whole family of Kähler metric, and each of those have a metric of SUN holonomy, right? So you can think of this as a family of SUN holonomy metric that you can get for a better way to define what we mean by the Kähler moduli space. Okay, the topological definition. Right now, it's a practical definition that the whole family of SUN holonomy metrics for a given complex structure will be the Kähler moduli space. Okay, we will see it in a simple example soon. But the other point is that even before you fix the complex structure, okay, think of Calabi-Yau manifold as a real manifold. Okay, suppose somebody has given a 2n dimensional real manifold. Okay, I told you that this 2n dimensional real manifold may admit different complex structures. Okay, and for each such complex structure, you can do this. You can find a family of Kähler metrics with SUN holonomy metric. So this family, okay, even before you have talked about the SUN holonomy, okay, the fact that regarded as a real manifold, you can put this whole family of complex structures. Okay, this is what is called the complex structure moduli space.
Are these Kähler matrix real?
Metric is always Hermitian, meaning G alpha beta star is equal to G beta alpha bar. Right? Because ds square should be real. Right? The metric components themselves are not real. Right? And that's the physical requirement. The G alpha beta bar start should be G beta alpha bar.
So what you are considering in this last statement is some real manifold, which can be written as a Calabi or
Yes, that's right. Real manifold which can always, where you can include complex coordinates. Right? And what I'm saying is that in a real manifold you can use different family of complex coordinates, and for each such complex coordinate choice, okay, you can put a Kähler metric, a family of Kähler metrics with SUN holonomic.
So there's a family of complex structures, and on top of that there's a family of
Kähler, exactly. Family of SUN holonomic Kähler metrics. Okay. Is this?
The string sigma model will know about this scalar potential through the metric of target space that will come in the sigma model.
So we are not talking about sigma model right now. Just consider normal geometry. Right?
No, we are not. But I mean, if we
Yes, if we do the sigma model, then metric will appear in the target as a target space geometry. Yes. Then if you want to study particle propagation or string propagation.
So in particular when a torus is regarded as a Calabi manifold, the family of complex structures is basically the space of tau.
Yes, so let me write down. I think that example will make it clear. Okay, what these various things are. So let's look at the example of a torus.
Also one question, when you say a manifold is a Calabi manifold, are you just using the topology, or are you also using the complex structure?
No. So it depends on your choice. Normally when you talk about a Calabi manifold, you are just talking about the topology. And then on top of that you have the whole complex structure moduli space and the Kähler moduli space.
So
at least from a physicist viewpoint, that's more natural. Okay, that you think of this as a real manifold. Okay, and then complex structure is an additional ingredient that you think of as a family of complex structures.
Yeah, it's something that admits a complex structure, which in further admits a
metric of SUN holonomic. Exactly, that's right. Okay, so let's consider torus. T2. Okay, so this I already said in the real coordinate system I write as y1 plus 2 pi y2, which is equal to y1 y2 plus 2 pi. Okay. Now we introduce a complex coordinate z equal to y1 plus tau y2. So space of tau gives you the complex structure moduli space. Okay. So now the metric, a Kähler metric for a given choice of z locally must be writable as del z bar t times dz bar. This is a Kähler metric. Okay, k need not be globally defined. Okay? You can cover it with different patches, and k, in particular, k need not be periodic under tau goes to tau plus 1 and or z goes to z plus 1 and z goes to z plus tau. Right? As z gets shifted by 1 or 2 pi, k can pick up holomorphic and anti-holomorphic terms. Okay? Because the metric should remain unchanged. So now the question is, what choice of k should we make to make it into SUN holonomic? Okay. So clearly we need a flat metric. SUN in this case is SU1, right? N is 1 for 2 dimensional. So you need a flat metric. Okay. Flat metric means that k can be some constant A times ZZ1. So this constant A, you are parameterizes in a moduli space. Okay, any value of A will give you an SU1 holonomial metric or SU1 holonomial metric. It's a flat metric, right? So in this case, the Kähler moduli space is one real dimensional, complex structure moduli space is one complex dimension. Parameters by tau. Yes.
But in case of like when we normally like metric, for some space-time metric, we doesn't care about any constant factor in front of it because we can always absorb some. In most of the cases, we can absorb it in some scaling of the coordinates.
But those scaling of the coordinates are not allowed here because if you scale z, right, then the periodicity will change. Right? So it's not true that for a compact space you can just scale it away. Right? Even in a sphere, a sphere of radius r is different from a sphere of radius 2r. Right? So it's they are distinct as metric spaces. Right? Topologically they are the same, of course. Right? But as a metric space they are different. Right? So in particular, if you have compactified string theory on this two-dimensional space, okay, then the metric on T2 will be parameterized by these three variables. Right? One is A, okay, the other one is tau. Tau has two components. Right? So this is basically another way of saying that you can take on a two-dimensional torus, you can take metric to be arbitrary 2x2 constant matrix, right? Constant symmetric matrix that has three components. Okay? Those three components are encoded in this constant A and tau. Is this clear? Right? If you write Z, say I have written it this way, but this matrix is just A dz dz bar. Right? Now you just write Z in terms of y1 plus tau y2, right? And write the metric in the y1 y2 coordinate system. Right? What you will get is a 2x2 constant matrix which is symmetric, and that's the most general parameterization of the allowed metric that you have on a two-dimensional torus. Okay, it's just that this way of writing it, okay, makes it gives a clear distinction between what is complex structure, what is scalar, and this is going to be useful in higher dimension. Okay, because for higher dimensional Calabi-Yau manifold, the possible deformations of the metric are not characterized by just constant values of the metric. Right? Constant metric is not an allowed solution when you are considering a complicated Calabi-Yau manifold. Okay? So when you are trying to understand what are the possible family of metrics that you can use on the Calabi-Yau, okay, this language becomes useful. Okay, I think I'll stop here and then we'll continue tomorrow.
From the previous lecture.
Yes.
So if I understood correctly, if we have type 2A, type 2B theory compactified on a circle, then at the level of supergravity, if I throw away all the Koldeban modes, then
they are the same. Yes.
Match, right? If I include these high derivative corrections, alpha prime corrections, still this statement is true?
Yes, still that this statement is true. Okay. You can show that at the tree level, these things match, and in fact, this because this is perturbative duality, this is also true for loop level.
Tomorrow's lecture is 5:30.
Tomorrow's lecture is 5:30 to 7.